Welcome back, everyone. So today we are going to discuss systems of equations, which is basically how to solve many variables with many equations. In your course, we are going to work with two equations and two unknowns. Of course, if you have one equation with two unknowns, you're not going to be able to solve for either variable. You can write one in terms of the other, but you're not going to be able to find real values. So before I show you a few methods, let me just remind you of the one we did in the previous video. We had two phone companies. One charges you, that's the pay. One charges you 5 cents a minute, and the other one charges you 4 cents a minute plus a $10 fee or sign-up fee or whatever. In other words, even if you don't speak, you're still going to pay $10. So think of this as y equals 0.05x, and this is y equals 0.04x plus 10. So two equations, two unknowns. And the question I had for you was, and I hope you can go back and watch that section of the video, what is the break-even point? Which means find a time so that the pay is the same, right? So we basically force the pay from company A to equal the pay from company 2, and we used some substitution, and we found that the time was, I believe it was like 1,000 minutes. Okay. And the other thing is there is a relationship that connects an equation that connects the temperature in Fahrenheit to the temperature in Celsius, as you know, right? And the question I had for you was, for what temperature it would not matter if you say Fahrenheit or Celsius. For instance, if water is boiling, you're going to get 100 degrees Celsius, which is the same thing as 212 degrees Fahrenheit. The two values are different. Is there a value, is there a temperature where it wouldn't matter if you say Celsius or Fahrenheit? For example, is it possible to say 20 degrees Celsius is the same thing as 20 degrees Fahrenheit, right? Is it possible? The answer is no. And how do we figure that out? We forced F to be C, as you know, and we substituted. We call this C because they're the same, or we can call this F, and then we solve, and we found that that temperature has to be negative 40 degrees. So we got F equals C equals negative 40 degrees. Now, whether you say Celsius or you say Fahrenheit, it wouldn't matter because that temperature is reflective of both units of measurements. Okay, so basically we were substituting one variable for another. That's what I did here and what I did here. So you're kind of familiar with it. There are several methods on how to solve systems of equations. There are at least 4 or 5 that I know of. I'm going to share with you 3 of them. One of them is called the substitution method, which is essentially what we did here and what we did here. So imagine I have a system of equations, two unknowns, okay? And we want to solve for x and y. The substitution method simply means either isolate x in one of the equations or y in one of the equations and plug that into the other one. I notice that y is already isolated here. So there is no need for me to isolate x or isolate y. I already have y being isolated. So I can go back to this equation, and anytime I see a y, I'm going to call it 3x minus 2. That is essentially what I did here. X plus 2, y, which happens to be 3x minus 2, equals 10. So that equation becomes this. You notice now that this equation does not have a y in it, which means I can solve for x easily. Before I continue, notice that I'm always putting brackets. And I know books don't do that, but this bracket shows dependency. In other words, you're not going to be able to solve for x or y just by looking at this one or just by looking at that one. These two have to work together in order for you to solve for x and y. So this bracket from the left-hand side shows dependency of the equations. So now, so here is the first equation where y was substituted for 3x minus 2. And I always carry another equation with me. You feel free to carry this one or that one here. So I kept this one here, okay? You don't want to just work with one equation. You always want to have two. Always two, okay? So I'm going to continue here solving for x. So clearly, this is 7x minus 4 equals 10. If you add 4, you get 14 divided by 7, you get a 2. And I keep carrying my second equation while I'm trying to solve for the first variable. Now that I know that x equals 2, I missed a step here, then you could say x equals 2 and y equals 3 times 2 minus 2. And then it takes you back to here. X equals 2 and y equals 4. And then when you finish, your solution set should be, first of all, it is a set, okay? And it's not 2, 4. You don't want to write this. Okay, this would be incorrect. It just means you have two solutions. One of them is called x equals 2, and the other one is called x equals 4. That's not what we're trying to say. What we're trying to say is how many pairs, or what pair do you have? My pair is 2, 4. And there is only one solution called this pair, 2, 4. You might say, well, can you have more than one pair? The answer is yes, if the lines are on top of each other. So you'll have infinitely many solutions. In any case, there is one solution, which is one pair. One pair. It is an ordered pair. X comes first, y comes second. So 4, 2 would not be correct. And you put a set notation to show your solution sets. Okay, so that's the substitution method. You isolate either x or y, and you plug it in the other one. The other method is called a linear combination method. And in this method, what you need to do, this is the same equation, okay? I'm copying the same one. You want both equations in the standard form. The standard form looks like ax plus by equals c. This is the very first thing you have to do. Okay, this is already in the standard form, 1x plus 2y equals 10. This is not, so that 3x has to go here. You get negative 3x plus 1y equals negative 2. Now, both of these are in the standard form. Now, the next thing to do is try to make either the x's or the y's to look alike. Look alike means one of two things. Either they look exactly alike, let's say you have 5x, 5x, or they're opposites. If they look alike, we're going to end up subtracting the equations. If they look opposites, we're going to end up adding the equations. And why do we do that? Because we want to eliminate one of the variables temporarily. We want to eliminate one of the variables temporarily. So, what can you do here? Well, you can multiply this equation by 3 so that this is 3x and this is negative 3x, and then I can add them up. I can multiply the second equation by 2 so that this is 2y and this is 2y, and then I can subtract them. I can multiply this by negative 2 so that this is 2y and this is negative 2y, and then I can add the equations. What I chose to do is multiply the top equation by 3. I put it in green. So if you multiply this by 3, you get 3x plus 6y equals 30. Now what I notice is these two numbers are opposites. So I am going to add them, right? I'm going to add them. I always show you what I do on the side. And if I add them, what's going to happen is the x is going to disappear. So you're going to get 6y plus y, which is 7y's, equals 28. And then again, dependency. You wanna have one of the equations that involve x and y. You could write this, you could write that, you could write this, you could write any one of them. I chose this one. I just dumped it here. Okay. Then I solve for y by dividing both sides by 4, and then I plug it back here. So negative 3x plus 4 equals negative 2, and now I'm allowed to solve for x. Okay. So minus 3x equals minus 6. And therefore x has to be 2. Once again, I got the same equation, 2, 4. 2, 4. Okay? So my therefore, this is the sign for symbol for therefore. The solution set is the ordered pair x comma y, x comma y. So this is called the linear combination method. Once again, you have to write both equations in this form. If you don't write them in this form, you're not going to be able to use this method, okay? All right, so the last method I'm going to show you, there is another one called Cramer's rule. You can work with vectors and stuff, but we're not going to do those. The third method is the graphical method. So this is where your favorite form comes in handy. I know you like this form. So this is where your favorite form comes in handy. You must write both equations in this form. Why? Because on the graphing calculator, you want to write y equals. The window looks like this. The window looks like this, and I'll show you. y1, y2, all the way to y10. So you have to have it in the slope-intercept form if you want to use the graphical method. So this is already in the slope-intercept form. This one, I got to move the x here first, negative x plus 10, and then I divide by 2. Make sure you divide both terms by 2. You get negative 1/2 x plus 10 over 2, which is 5. Now, both of these now are in this form. I call them y1, y2, so we differentiate between the two. So if I have two students by the name Jane, I might call them Jane 1, Jane 2, right? So we know the difference. And in this, after this, you literally graph them. And I'm going to show you how to graph them. You go to, turn on your calculator, you go to y equals, you put the first equation, this one, and then you put the second equation here. Okay, you don't need the other ones, just these two. And then you can immediately go to graph, and you might see the graph. If you don't see the graph, that means your window is not good, and I'll explain. So imagine the two lines are here, and your window is here. This is your window. You're not going to see anything, are you? So imagine your window is here. You're going to basically see this piece. And you can say, oh, you know, I only got one line segments. I'm supposed to get two lines, right? I only get one line segments because your window is messed up. So what we want to do, there are two ways to fix the window. One is to basically go to the window and play with your window. You have an X minimum, you have an X min, X max, Y min, Y max, and make sure that you have a nice window. So this is called your X min, this is your X max, Y min, Y max. So pick some numbers, let's say negative 10, 10, negative 10, 10, and you might get a window like this, and the lines might look like that, right? And you say, oh yeah, I think I can see both lines, I can see where they intersect, and basically that's your solution. I can do that. And if you need more space here, if you want to see more here, then you have to increase your Y max, right? You make it 20, so it goes up. If you want to see more on this side, you can increase your X max. So let's say 15, so it's expands on that side. You play with the window until you see equations, lines like, you know, like this, okay? Another way, which is shorter to do, is you click on zoom, which is to the right of window. Let me erase this for a second. You click on zoom, and you'll have, there are two good options for you. One of them, I think it's zoom 4, and there is a zoom 6. I think zoom 6 is standard. And what zoom 6 does, it gives you the window that I just explained, negative 10 to 10 and negative 10 to 10. And zoom 4 goes from negative 4.7 to 4.7, and from negative 4.7 to 4.7. There is a reason why 4.7, not just 5, because the pixels work in multiples of 4.7. So if you really want to have a nice window that looks like this, you want to go from negative 9.8 to 9.8 and negative 9.8 to 9.8. Anyway, generally one of these two would work for you, and then you click on graph, and hopefully you will see the graph. And if you see the graph, when you see the graph, what you want to do is click on trace until you find the intersection, and I'll bet you will find the points 2, 4. I'm going to spend more time on this in class to show you exactly how to capture this point. So these are 3 methods on how to solve systems of equations. We will practice them all, and you'll become good at this. And why do we care? Because we want to be able to solve, making a decision on which phone plan to use, figuring out the temperature for which it wouldn't matter whether you say Celsius or Fahrenheit, and solve many other problems. We call them optimization problems. All right? Take care.